Hello, everyone. My name is Bekkouch Imad Ibrahim, and I am currently doing my PhD in data science or in artificial intelligence in Paris Sorbonne University. And today, as part of the REPA Machine Learning Conference Week, we will be just seeing a small tutorial on how to build object detection models for edge devices. So the aim of this object detection model is to be very fast, but still as accurate as possible. After we finish the presentation of the different components of our model and how we're going to be training it, we will be spending the rest of the talk on how to use Kubeflow to orchestrate the training process of such models. If you have any experience with Kubeflow, you're going to understand that it's very difficult to use or to start with, to start coding from scratch directly using Kubeflow. So it's always a very good behavior to start on some sort of a notebook, preferably on Colab, so you would be able to just quickly get started by running. After you finish all the code inside Colab, then you should start migrating into Kubeflow using just small containers for every single task, and then linking those containers together using Kubeflow pipelines. So in today's talk, we will be speaking about YOLO v4, which is an architecture from the YOLO family, which is meaning you only look once. So usually they are considered to be the fastest family compared to the RCNN family and faster RCNN and mask RCNN architectures, which are implemented in Tektron. Usually these models perform very well, but sadly their size is too big for edge devices, and they are too slow for such utility. In here, so basically we will be speaking a little bit about what YOLO v4 is, the architecture of the model, and how can we configure and train such models on Colab first, and then we will be sending it into Kubeflow. The structure of the talk will be as follows. So first we will be speaking about how do you understand your GPU or the hardware you are using, and how to get this arch value, which is very much needed for compiling and configuring or making the Darknet installation. Later on, we will be speaking about how to download and configure the makefile, making Darknet after that. We'll also be using a public dataset from RoboFlow, which is a very useful website. I find it to be an amazing website for data conversion for different formats. And usually they come with very useful or easy to use Colab links for training every type of object detection model, I think. So they have object detection models for YOLO v5. So they have Colab links for YOLO v5 and PyTorch for different versions of YOLO v4. So basically, YOLO v4 or the tiny version or the scaled YOLO v4 version. I think they also have stuff for YOLO v3 and for some other smaller models or lesser known models. So it's always very nice to start using their Colab links as a introduction to this model. And usually they also provide you with a download link for a downloadable dataset in each format. So basically, if you upload your dataset in a specific format to RoboFlow, you can later on download it in, I think, 7 or 9 different formats. And if you are familiar with training object detection models already, then most of the time you'll be spending on converting the dataset from format to another. It's very hard to keep track of all of the JSON files and TXT files, and whether the boxes are being made using the X and Y center coordinates, or with the height and width, or with the 2 points of the top leftmost point, or the right bottommost point. So it's usually very difficult to make these conversions and configurations. So it's always very useful to start using such websites that facilitate testing, at least to get started with these models. Later on, you can, if you're in a company, you can have your own code for that and create, for example, a custom container as part of your pipeline to convert the different data sets, right? Data formats. After that, we will be speaking about configuring a custom ULOv4 training config for Darknet. And then we will, of course, do the training. You'll see that this training step is the easiest. For me, I would say the hardest part would be encoding, would be the following stuff. So basically configuring your data set and configuring the config of ULOv4. And if you're not using something that is already configured for you by some DevOps engineer, then probably you're going to be spending a lot of time in here just to get the correct values for your hardware. And the last part will be just to load the trained model and test it on a couple of images, right? I see in the chat. Could you, yes, I was going to do this exactly right now. That's a great remark. Let me share the I will share it on the chat. Please tell me, guys, if you can see it or not. I think this is the best way to share it.
Yeah, we can have access to the tags.
Nice. Let me also send it like this. I believe that now you guys should have the link already. So please just open it in your favorite browser, preferably in Google Chrome because it's more compatible. But you can also do it in Safari or something else. Just a quick introduction about me. So I did my bachelor's in networks and distributed systems in Algeria. Then I came to Russia in Innopolis to do a master's in data science. And finally, now I am in Paris doing my PhD in artificial intelligence with the Sorbonne University. When it comes to industrial experience, I've worked with Provectus as a data scientist for 2 years. And also I've worked as a research scientist at the Industrial AI Center at Innopolis for 1.5 years. Just a small introduction on the type of projects we work on in Provectus. Let me share it here. There you go. So this is Provectus, the company, and most of our projects, you can find them at least if they are publicly accessible in the, what is it called, in our website. Personally, I've worked on the worker health safety project and the, intelligent worker safety and access control product. The worker safety product mainly focuses on detecting, for example, hard hats and vests, and just making sure that the safety guidelines are being followed inside the construction sites, for example, and areas where there is high risk or high danger on the employees. Usually, to do these to do such tasks, you should probably always have a on site. So basically, you will have some deployed models on the edge in either your own, for example, nano devices, or sometimes you can do it on the cloud. But I really haven't seen many of our clients asking for on cloud deployment of the models. So usually all the models must be deployed on their hardware and basically processing the videos and sending the data, processing the videos, analyzing the images, and finding if there are some violations, and then sending the data for storing them in either the cloud or just locally in their interface, right? The main difference, I think, between these two products, this one uses another thing, which is, for example, for COVID-19, one of the main concerns is not just detecting how many people are in your store, but for example, if you are in a closed environment, then the challenge would be not just to count how many people are there, but to verify that they are following social distancing rules. So in these cases, you will find, yes, basically you'll find object detection models coupled with other algorithms to calculate the distance between these models and make sure that not just the masks are being worn correctly, but also other safety guidelines are being followed, such as social distancing. In this talk, we will actually see a very similar example to what we usually do in our company. The code will not be the same. So basically, I will not be showing the same type of models we use at our projects, but you can think of the same architecture. So basically, if you change the models, change a little bit the code, it will be kind of the same thing. So it's the same way of thinking. By the end of this tutorial, you should be able to make or to create a very small size, for example, 23 megabytes, I believe, model that is able to do parking lot, yes, free spaces parking lot detection. So basically, it will be able to detect the empty places inside a parking lot, and this can help you just handle or manage your parking lot much easier. Again, the dataset is available publicly on RoboFlow. I will just show you guys the RoboFlow website and how can you use it. It's very useful if you want to build your own portfolio, for example, and showcase it on different datasets. So here you can come and see the different datasets that they have. So for example, here is for some aquarium data and annotating the animals in there. There are some annotations for chess pieces datasets. And this is for some, if I'm not mistaken, some cells inside the blood. Moon dataset, yes, and others in here. What we are interested in is the following. So it's the parking lot dataset. It contains lots of images. So it's going to be a little bit more difficult to train or more time consuming to train it. But the results will be very good, as we will see very soon in the end of the session. We will be doing the mean average precision evaluation of the model, and you will see that since the data set is pretty big, even the model size was small, it still gives very good performances. Again, if you want to just do something easy to work with, you can go with the small data sets such as the chess piece dataset or the aquarium dataset. I highly recommend, if you are following this tutorial and doing it your own, please try to change the dataset from the start. So basically, do not download the parking lot dataset, but go for something else. For example, the chess pieces dataset, and fix the code as you go. Just like this, you will be able to learn even better than just watching and doing the same thing as we are doing here. To download the dataset, you should just come here, press download, and basically it will propose to you a variety of different formats for the dataset. Just to take an example on how the annotations are made. So here are the annotations, the images, as you can see. We have in this dataset, I think, yes, two classes, and this is the distribution of training, testing, and validation. You can also configure this split however you want and make it random or not. The different available annotations are the following. So there is the YOLO Darknet TXT format, which is the one we'll be using. There's the scaled YOLO v4 format. There's the YOLO v4, but in PyTorch implementation. There's the YOLO v5 PyTorch implementation, which is, I think, the main implementation for YOLO v5. And there's the TensorFlow record annotation, which is also very important for if you will be building what are they called, object detection models using TensorFlow. So for our purpose, for the purpose of this tutorial, you should go ahead and press YOLO Darknet. And you can either download it locally, or I prefer to do this show download code. It's much easier. And basically, you can either copy this code into your terminal to download it locally, or basically following this command or putting this command inside your Jupyter notebooks or inside your Colab links, right? So yeah, let's get started. The first step, as we said, would be to understand your GPU. Let's connect first to a Colab. The default runtime that I'm using already uses a GPU accelerator, but if it's not for you for some case, please just create a copy of this notebook locally on your Google Drive, and then choose in here GPU accelerator. It will make things much faster for us. So the first step would be just to make sure that the installations of CUDA and QDNN are correct. This will be very helpful for you later on to understand what kind of architectures you will need. But the main part of the code that you should be writing is the following. So basically, every GPU has its own parameters in here. So the GenCode architecture and the code. So preferably, if you are going to be using one of these GPUs, this code should already give you an idea or give you a good name, or let's say the good start for the values of these variables, or these parameters for the makefile. But if you cannot find your GPU in here, then in most cases, it's quite an old GPU, and it might not be able to run Darknet. But just in case, please just go ahead, put the name of your GPU in Google, and add the word after it, for example, Arch and code. And you should be able to find a link that gives you these values for your GPU. So as you can see here, Colab has provided us with a Tesla T4, and this is the Arch value for it. Usually what we'll be doing is copying this string and going to the Darknet implementation. Let's see. Let's first download Darknet or git clone it. In here, you will see that I'm git cloning the RoboFlow AI fork of the Darknet. In most cases, you might want to go to the Alexei AV implementation. It's much cleaner, but I find it to be, I would say, overwhelming for beginners. So the README is very detailed, and you will most likely find all your questions inside the README. But if you're just getting started with YOLO v4 and Darknet, this README is quite a mess, and it's not really beginner friendly, I would say. So once we finish this tutorial, preferably do not use the RoboFlow implementation. It's the same, but they just have some simplifications over this one. Preferably, if you're going to use this in the industry, always go directly for the Alexei AB Darknet implementation, as he was the author of YOLO v4. So here we can check that we have git cloned the Darknet repository. The very important file would be the make file. I highly recommend to have this Darknet cloned or forked inside your own company's GitLab or GitHub, and setting these values for your project. Because usually later on, if you're going to be configuring it inside of what's it called, inside of Kubeflow as part of the pipeline, it will be quite a mess to change the content of the file and changing these configs. Because later on, it's going to be a little bit more difficult to do it, because you will not be able to do it visually like this one, like this. But the most important parameters that you should keep in mind are whether you have a running OpenCV installation. Usually, if you are going to do it on Colab, then everything is already configured for you. If not, then you should probably install OpenCV from scratch. So basically from source by compiling the source code and providing the installation using a environment variable. Because it doesn't really detect the Python implementation of OpenCV. So usually you should compile it by yourself, right? The two others would be whether you're going to be using GPU or not, and whether you have a correct installation of QDNN. Once these three parameters are done, so basically 1 for active and 0 for not active, we should focus on the second most important variable, which is the architecture variable. And for us in this code, this value will be set directly from here because we already set it in the environment variable arch value. So let's run that step and see what happens, right? So again, here's the makefile. Now let's run this config for the makefile and see what changed. So currently, as you can see, it has already started the make. Basically, we went inside the folder and now we are compiling and making the Darknet implementation. I just want to make sure that there were some changes in the value. Let's see. It should be the full. So compute 75 and SM. Let's see. There you go. Not this one. Or is it this one? I'm not sure, but it should be somewhere here. It should be added somewhere here. The correct arch compute value and code SM value. Let me check where was it added, because right now the model is still compiling. Let me see. I can't really find it right now, but it's written somewhere here in this file. So now, as you can see, the compilation was successful. This does not look like a successful compilation. As you can see, it's a lot of very ugly output, but just trust it, it's the correct installation, right? The second step here would be to download the correct weights for your model. Before doing this step, I always recommend to, first of all, decide what YOLO v4 implementation you will be using, or what YOLO v4 size you will be using. There are three main different YOLO v4 sizes that I like to use. First one is YOLO v4 TSP. The second is the YOLO v4 tiny implementation or a tiny version, and the YOLO v4 as it is, right? So the smallest one is the YOLO v4 tiny implementation. And we can come here and see it in this config file described both in hyperparameters and in the layer definitions of the model. So we can see here it's composed of several convolutional layers with different activations, tried, filters, and everything else. And most importantly, we will see, yes, and most importantly, we have some YOLO layers in here. The YOLO layers, or what's called in here the YOLO layer, is the layer which is responsible for the classification. Please remember this layer. It's very important because it's going to be very influential on your own data set. So basically, we will be changing the values in all of the YOLO layers. It's always very important before going further and understanding how to change this architecture. Preferably, I would like to just quickly show you guys what is a typical architecture for YOLO v3 or YOLO v4 model. Let me show you here. So I find this link to be very good as a starting tutorial for what YOLO v3 and or the YOLO v architecture is. So just to come and see it here in general. So you can see that the input goes through a set of convolutional values. let's go to the final detection part. So once it arrives to the final part, usually the size of the feature map or the output of this convolutional block is much smaller than the input image, and hence it will contain information useful for detecting bigger objects, right? And what they will later on do is they will take this, what is it called? They will take this feature map, output feature map, and upsample it, concatenate it with the previous layers, and basically do the same task again of object detection. But in this case, we are seeing a bit bigger feature maps, and it's more useful for detecting medium-sized objects. And later on, we will take this feature map, and this feature map, usually it's a bit bigger than the others, and hence it's much more useful for detecting smaller objects. So basically, a YOLO v4 or YOLO 3 v3 architecture takes several parts of the input image of the pipeline in here and send them for detection. So in total, we will be having 3 layers for detection in our YOLO v3. One is for big objects, one is for small objects, and one is for medium objects. Another very important thing to understand is how is this detection happening. So basically, in that feature map that we have just spoken about, every single pixel will contain the following values. So every single pixel will contain information about the object that either exists or doesn't exist in there. So the information will be the following. So the class label, and hence it's, for example, if you have 5 classes, then here you will have 5 different values, right? The objectness score, this is just a value to tell whether there is an object inside this pixel or whether there's an object centered around this pixel in the feature map. And the other coordinates, the other values in this array would be the box coordinates, which is the center of the object in here and the width and the height of the object. Yes, YOLO v3 and different versions of YOLO v4 come with the following structure. So inside of every single pixel inside that feature maps, inside these 3 feature maps that we have just spoken about, so the 3 scales of feature maps in here, inside every single one of their pixels, you will be able to detect 3 objects or 3 types of objects. Usually each one of these objects will be able to, each one of these 3 boxes. So you see each box contains the following information. Each one of these boxes is set for either a horizontally laid object, a vertical object like this one, or a rectangular object. So that's why we have 3 boxes at each pixel. So basically for each pixel, there are 3 boxes. Inside each box, there are these values. So I guess this is the most important part to understand about YOLO v3 or YOLO v4. So this is just another example to show you guys. So for example, here in the final layers of the model, you'll see that the number of pixels is much smaller here. So you'll be able to detect bigger objects. In here, the number of pixels is a bit bigger, so you'll be able to detect medium objects, and here you'll be able to detect even the smallest of objects because the resolution is similar to the original image. Now let's go back, and as we said here, very important to configure is the number of classes inside the YOLO layers. So this one depends on your data set. So for example, in our case, we have 2. And another one would be the amount of filters in the convolutional layer that is right before the YOLO layer. This is very important, and this is the reason why we did the explanation of the YOLO architecture, because this value should be set to a specific formula. Let's check the formula together and understand why this formula is made. So if we come back here to this example, let's see. Yes, if we come back here to this example, I would like to show you guys the demonstration of how this formula exists, right? So let's say here we have a number of classes, right? Number of classes plus 5, which is, for example, which is the number of added attributes to this array, which is for objectness score and the 4 coordinates of the image. So it's NC plus 5 times the number of boxes that are able to be predicted inside each image. So as we said, for different YOLO versions, this value is set to 3. It depends on how many anchors you have. And this is basically the formula that you should be using to setting the, let me remove these, nice. So this is the formula that you should be using to set the number of filters in every convolutional layer that comes right before a YOLO layer. This is very important, and if you don't do it, you're going to run into many compilation errors. And sometimes if there are some people who just go and change all the filter values of all the convolutional layers, and this usually leads to very bad performances. So it's always very important to only change the filters value of the convolutional layers that come right before a YOLO layer. So in our case, for example, we have 2 classes. The number of filters should be 2 plus 5 times 3, which is 7 times 3. I'm not sure how much that is, but I think it's 21, right? So basically here, the number of filters should be 21 in this case. Yes, I think there is another YOLO layer here. So here is another YOLO layer. So basically you have to change the number of classes, the number of filters. Only inside this YOLO v4 tiny implementation, there are only 2 levels of detection, object detection. But in all the other implementations, you should find 3 levels of detection. So let's come here, for example. Right, so this is the first level, second level, and the third and final level of classification. Yes, now once we have selected the architecture that we want, usually it's very much preferred to find the pre-trained weights for that architecture itself. And this is a very difficult task sometimes. If you are lucky and you will be using a architecture that is commonly known, you can come to this Alexei AB Darknet implementation and find it here in the README. Let's check it together. It should be in the beginning, I think, right? Let me see. Yes, here are the pre-trained models section. And basically, depending on the config file that you will have, you will be able to find the weights of that model. So in our case, this is the architecture that we want. This is the config file that we want. And here is its corresponding weights file. The output would be, the pre-trained model would be 23 megabytes. In our case, after we finish the training, the size will also stay the same. But sadly, in most cases, you might want to try or experiment with different, what are they called, with different architectures, with different configs. And in these cases, you might not find your weights file in there. So it's always very useful to come section. So basically the releases section and go directly to the assets folder. And usually in here, you'll find many more weights. And yes, depending on when was this architecture included, you will find its assets in that area. Enough about the configuration. So now let's go to now we just downloaded the weights. So here you can see that there are actually 2 different weights for the YOLO v4 tiny implementation. This one, you can find it easily in the README. I think this one, you can find it in some PackMD website that Alexei AB has provided just for the weights, but you can also find it in the assets of the releases. Now let's go to download our data. Again, remember, this is, what is it called? RoboFlow. We come here, We check YOLO v4 Darknet, download, copy this code that we get, and basically we will put it here. Right. And there you go. So there it will start the download. We will get the data. We will just check how the data is and how does it work. Before we get to the next parts, I would like to start by doing the training, so that it would be faster for us later on. So I'll start by running the content of Colab link. Nice. So here is the dataset downloaded. We can come here and check the dataset looks like. This is a very important step also. So basically here you find the validation data. It's pretty large, I think, right? Let's check. You will find every single image accompanied with a TXT file. Let's check. This would be the TXT file, right? Yes. So basically inside the TXT file, every single line corresponds to a different object in the image. The first value will be the index or class of that object, and the rest would be the coordinates of the object. How do you find the name of the classes? Usually there is a separate file called object.names. Let's check where it is. In our case, it's here. Object names, here it is. So basically we have two objects, two classes, space empty and space occupied. If you feel like the name is too long and basically the final visualization, right, would be a bit ugly in here, so you see it's overlapping, then you should just, for example, make it like this. Empty, occupied, right? Save it, and usually this would be, I think, easier to visualize. Nice. Now the second very important file that is related to your data is called object.data file. And inside this file, let's check it out. You should be creating it for your dataset. It contains the directory of, or it contains the file path for the list of images for validation and the list of images for training that you have. It contains the path towards the object.names file that we just described, the number of classes that you have in your model, that you have in your dataset, and the backup, or where you will be storing the final weights of YOLO v4. So basically, this is this is what you will be sending to the training, right? Now we will speak about the config file and how to configure it. We already spoke about it. So here we get the number of max batches. Max batches, if you are familiar with training images, training models for classification, max batches is equivalent to what is it called? To the number of epochs if your model, so, or the number of iterations in this case. So basically, this is the number of iterations of your model, or how many batches will the YOLO v4 implementation be loading from the disk until it finishes the training. There is another one called steps. In steps, usually it's just a way to indicate to YOLO v4 to start saving the weights of the model, while when it reaches 80% of the specified number of epochs, or 90% of the specified number of epochs. Usually it's specified as a string like this one. And remember what we said about the number of filters, which is number of classes plus 5 times 3. The 5 in here is for the objectness score plus the coordinates, and the 3 in here is for each different anchor inside every scale of detection in YOLO v3 or YOLO v4 implementations. This code is very, very nice because it usually helps you to change this config file using code. I would also, again, recommend to change this config file either using your own Python implementation, so basically create a component that does the configuration, or just configure it locally inside a GitHub repo and then build your components using these GitHub repos for your own project. Just to confirm in here, so our YOLO layers should start soon. Yes, here's the YOLO layer. We changed the number of classes here, and we changed the number of filters in the convolutional layer that's right before a YOLO layer. So for example, the rest of the filters will stay the same, but this one will change. Nice. Just to make sure how the file actually came out to be. So here we have max batches equals 4,000. Number of steps is the following. This is the number of steps for training. And you can also change the learning rate. Height and width are also very important values to change. And the batch size and the subdivisions of each batch size. These are also very important parameters to change. Here we can see the YOLO before training. I think it will not be able to train during the time of this talk, but we will skip this step and just see how it's done later on. So basically, the training starts by reading the config file. So here you can see the different layers of your model. So config, convolutional layers followed by batch normalizations and stuff like that, right? Max pooling, some YOLO layers in here, and there you go. YOLO layer, and here are the next convolutional layers, and then followed by the second YOLO layer. In most cases, you will be finding 3, but since we are using the YOLO before tiny, we only have 2 of these YOLO layers. And then it should read the, well, I think it should read the pre-trained weights in this area. I'm not sure why I did not. Let me check, or why I did not speak about it. Or maybe it spoke about it somewhere else, but let me check. Yes, here they are. Loaded 29 layers from the weights file that we provided. It's very important to check for this message because sometimes most of the errors that you will find, or the errors that you will not find, is you attributed the wrong weights for the configs. And this is horrible because Darknet will not give you any warning or any type of error saying that this weights file is not the correct one for this configs. It will basically just ignore the weight file and start training from scratch. And usually this will give you very bad results and you will not even see the reason why. So please always look for this line of correctly loading the weights file and training from them. After you finish this reading, you should start doing the training. And here you can see the training happening, followed by the calculations. I think I'll stop this one right now. And yep, let's stop it. Let's go back and change the max batches just to, for example, 200 or something like that. Let's do it. 200, run it. Verify. And go. Let's no. Oh, I think I should have continued the training on the output of this one. So basically, you see in here, this is the first weights that we have saved during our training. Let me see how much time will it take. It should take 7 minutes to finish. Let's skip this step and go to the next ones. So basically, if you'd like to test your model, usually there are, so for example, to apply some detections on some images, basically we will take some random test image and send it through the model to do the inference using a Darknet. You should always keep the same config file used for training and use it for the inference. This is a very important thing to do. So this is not the case for example, image classification, where you just take the weights of the model directly and just load them, for example, in TensorFlow or PyTorch. It would be helpful to have the implementation of the model or inside that code, but in most cases, you just need the weights of the model directly and it's running. But in this case, when you're using YOLO v4 Darknet implementation, you should always have the same config file as the training. And then basically just send it the image path and do the task. I think we have 10 more minutes left for speaking about how to use Kubeflow to run such models or to do this training. As you might expect, so this step would be very easy. I think the most important thing that you guys should take from this talk is how to do the configuration of this config file for the YOLO v4 and understanding the reasoning behind the number of filters for each layer and what to change and what not to change, right? Let's hope the training would finish soon. Yes, it's 4 minutes left. So basically to see how a, to see how a model in Kubeflow would do this job that we have just spoke about. Let's check this, for example. Yes. So I always recommend having the following. So a separate file for your pipeline. Inside the pipeline, you should have this information. So basically, you will be of course, you will be importing KFP, which is just for Kubeflow, and it will allow you to do the following. So you define your pipeline as a function. It will have some inputs. So these are the inputs to your pipeline. And then define the next steps or define the steps of your model as different function calls. We will see how each function call is made, but the important part would be how do we connect these different components with each other. And we do that using the following. So basically this step, so download file from S3, you give it the file path and it basically will download it and put it in some temporary output that Kubeflow, temporary output folder that Kubeflow will generate for you. And you can access it using the .output parameter here. So once you get this .output and send it to the next steps, as you can see here, this would create automatically inside every single one of these containers a new temporary folder for input where it will contain the downloaded files from this step. This is very important, and let's see how these components are made. 1 second, let me just, yeah, now we're calculating the mean average precision score. That's amazing. So basically every single component should be described as a .yaml file. So for example, let's take this one. This is a very good example. In this example, we have the following. So you give it a name, a small description about it, inputs and outputs. This is a very important thing. So the input path, the input is the S3 path. So for example, S3 // I don't know, some what is it called, some bucket in S3, and then the path inside that bucket. And here you have the name of the container or the image that you will be using. If you have some sort of your own local registry, then usually use it, or you're using ECR in most cases if you're using AWS environment, so S3 and these things. You should have your own, yes, ECR in here, and the links to your compiled Docker images, or yes. You should have the command that you want to run. So basically Python, the name of the file inside the container that you want to run. And if you have some parameters to it, just send them. And here are the args. A very important thing to know is that output path is not something you will be configuring by your own. So it's basically something that will be created by Kubeflow for you. And you should just use this one as an argument for your main function, or for your main file, for this function inside the main file. So basically you should use this one as just your path towards or your output path, and put any file that you would like to send forward to the next steps inside this path. So do not create this path, just use it directly as if it was created in your own code or created locally. Later on, how will you be using this path is the following. So basically, here's train classifier. So you can see that we send it the train path, validation path, and target names. So these paths are what was used before. These are the output of the previous steps, and we use them in here as just inputs to our container, and then we send them, here you go, to our a new container in another area. And these files, or the content of these files, will be copied from the previous containers directly to your new containers as if they were made locally. So basically, everything you will be using is local. Yes, is local. So basically, you will be using your local file system and sending files between different containers easily just by specifying the dot output and sending it from component to another. Let's go back to, let's go back to the pipeline definition and just see how it's done. So again, we have different steps, different outputs, and basically the output steps. So you see, validation step is the input for another step. Training CSV is the input of another step. And all of these steps basically are just containers that are built and pushed inside your own ECR or Docker Hub. And basically, you just load these containers. So not this one. So basically, you will be loading these containers from here. So we'll be loading them from their YAML files. So let's come to these definitions for a file. So inside this definitions file, usually you should just put one function to read the YAML files and just load the steps using that function and save them all inside one Python file just for easy access. And then you can create several pipelines in your code like this one. Usually you should have different types of data augmentation, data validation, or sometimes you will have the same pipeline, very long pipeline that does all of these tasks. But yes, that's something that you should decide. We still have some 5 minutes. Let's go back to the code here. I think, oh, it's still calculating the mean average precision score. But as you can see, the training has finished. Let's see if there is any. Yeah, sadly. So basically, we just trained for 200 iterations. It's not enough to fully train a good model, but let's see in here. Let me refresh. It should save the weights actually after calculating the mean average precision score. Yeah, sadly, the validation, the test and validation data sets are quite huge in this data. That's why it's taking a lot of time to finish the calculations. But yes, let's consider this step finished and start answering some Q&A until basically this result comes up, and we will speak a little bit about how to interpret the mean average precision score. It's a very important score, and sometimes interpreting it gets tricky. Do you guys have any questions so far about how to use Kubeflow to build these pipelines, or about the code that was previously mentioned, the config files, where to find the weights, the data formats, all of these things? In that case, I think we can finish. And what will be the output of this text? So basically, it's it's going to be a small evaluation text for your model, basically different precision, recall, F1 score. I think also, yeah, the mean average precision at different thresholds. Yes, and I think that's it. Just all of this in your output. You should find something in here also for the chart of training. But since we did the training twice, I think this chart would look a bit ugly. Yeah, the chart looks horrible. Let me see. But yes, so basically the chart, if you do the training correctly and you keep it, for example, for 8,000 iterations or 8,000 epochs, you should find the loss function going down a little bit like this with the output, with the passage of iterations. and you will see the MAP score going up like this. This chart is very useful just to make sure that your model is actually training and the learning rates that you chose are actually useful and they're not overfitting or underfitting, right? Yes, I think this is the main part of the talk. Usually after we finish this calculation, you should have a lot more files here for the backup. Yes, it's an amazing question. How to specify such that you neither overfit and underfit? So basically, Alexei AB, who is the creator of YOLO v4, recommends that you at least have 2,000 times the number of classes. So in our case, we have how much? We have, so we should 1,000. But he says also the minimum amount of epochs should not be less than 6,000. So usually either 6,000 or 2 times the number, 2,000 times the number of classes. So this is the best way to set your max batches value. It's not too much and it's not too little. So usually if you have a big data set like this one, it should take you around 7 hours to fully train your model. But once it's done, it will be a very good model. I think training a YOLO v4 completely, not the tiny version, should take you around 13 or 14 hours. And for some reason, YOLO CSP always takes a bit more than that. Do you guys have any more questions? And Christopher, did I answer your question? No, it does not use early stopping. No. So basically, it trains until it arrives to what is called the end of the implementation. But it will be calculating the mean average precision on different steps of the training. So basically, for example, after 200 epochs, 400 epochs, it will evaluate your model. It will always save the best weights in here. So basically, you will have the last weights, you will have the best weights, you will have the 6,000 weights, so the 80% weights, the 90% weights, and the 100% weights. So I think you should have at least 6 weight files, and always use the weight file that ends with best.weight. Do you guys have any more questions, or should we call it a day?
Seems no more questions so
That's
far.
nice. If you guys have any more questions or something like that, you can just contact me directly. I think you can find my wonderful presentation. Thanks a lot. Thank you so much. You can easily find me on just Google, just Bekkouch Imad Ibrahim, and you would find my LinkedIn. Contact me directly, and I will be more than happy to answer you guys.